This clip is to show you how to use the modular panel tool on the PCP-AGH toolbar in Grasshopper. The tool is meant for flat paneling a unitized system on a curtain wall facade. By unitized, I mean each panel has the same width, and then depending on the logic of generation, it might be a straight up panel vertically or a leaning panel that follows the geometry of the surface. So I quickly made a double curved surface in the Rhino model, and I am going to reference that with the B-rep component in Grasshopper. So we can move to the Reach tab and find the modular panel component. Drop that on the canvas. You can see the B input takes in the B rep, which is the surface that we have. And the elevation input is really the elevation locations for your stack joints. What it will do is internally intersect the B rep to get a bunch of stack joint curves and subdivide those curves with the module that you provide. So in order to get a kind of an uneven look for these stack joint locations, I am using a series component and a graph mapper just to redistribute the numbers in a sort of organic way. We can put that into the elevations. And the D input, D stands for distance, is really the module distance. We can use a panel and type in quickly the distance that we want. Let's start with 15 so that it doesn't take too long to compute, because the more panels you have, the slower it will get. As you can see, the bottom row is way too squished. Let's change the graph mapper so the differences aren't so distinct. So now let's shrink the panel so that the proportions is more realistic as a curtain wall panel here. If you zoom in, by default, the panel is probably on tiered cake. Essentially, on each stack joint location, you do the intersection curve, and then every module you have this width, and then you extrude it straight up. Alternatively, you can use the leaning flat method, which, if you uncheck the tiered cake, you will see these panels would kind of fall backwards or forwards to follow the geometry. You can also reverse the stack joint curve direction. This way, the module or the unit, so to speak, starts pushing from the other end of all the curves. For the purpose of this video, we can just set it back to the original one. I think everything is pushing from the left to right. And if you zoom in, you can see, because it's leaning and to guarantee flatness, there is a bit of a angle between each panels, and then the component actually gives you the analytical points from which you can get the deviation between each panels. To better see it, let's bake these panels. You can see how it follows geometry, yet each panel is slightly at an angle from the next one. So we really need those white dots to kind of calculate what that gap is, and whether that gap is within the tolerance of construction or the tolerance of a mullion. There is an optional input C on the module component. It is compensation for mullions and differences between the panels. You can input a number, and that way it can either shrink or expand the panels one-dimensionally. It takes a little bit of practice to understand what I'm looking at. I think I need to change it to a negative number. So let me disconnect that so it's faster. I think if I do negative x divided by 5, that's more of a to-scale number. In case you don't see it, let's bake those panels, and there, that's what it means by compensation. right now it's a negative number, so it really just shrinking each panel in that one dimension. It's an optional input. We can ignore that if you want to. So for these points to work, it really needs to be in pairs. The top left corner of the first panel needs to be paired up with the top right corner of the next panel, and obviously the first panel and the last panel don't have a panel before it or after it, so we need to get rid of those orphan points at the beginning and the end. And what I can do is using this call index component and take out the 0 index and the -1, which is the first and the last. Just making sure, make sure your W input is on true, so it wraps around the list. So now that I eliminated those orphan points, each point just needs to be paired up. Right now, each row, it's on its own flat list. So let's use the partition component to divide them into groups of 2. And for simplicity, let's simplify that tree structure. And you can see the first index represents the row of panels, and then the second index is really each pair. And of course, within each, there are 2 elements, point A and point B. We can use a list item to grab the first and the second, which are the only 2 that there is, and then use the distance component to calculate the point distance between those 2 in each pair. And let's use a graph mapper, a path mapper to trim the excess of tree structures. And now each branch is corresponding the row of panels. A point, of course, will not work. This is actually numbers because it's a distance. So each list is that row of panels. The first number means the difference between the first panel and the second panel. So let's sort each of them and get the largest number, because we're mostly interested in the maximum deviation. Again, using the list item component, get the last one. Let's look at each one. Okay, those are the numbers, and like I said, they correspond to the panels, the rows of panels. There's the content. Just so we can look at it in a clearer way, we can use a tree branch component to sort of cycle through each row and see how they're corresponding to each other. And of course, let's simplify that so that the tree branch component can recognize it. When I just put in the number, trees go into T, and then the numbers or the deviations go to the other one. And we can use a slider, say 0 to 1 or 0 to 10, and put that in, disable the preview on that. So now you can see as we scroll through the slider, you can see each row of panels would correspond to that deviation, maximum deviation of that level. So this is really helpful to quickly get a way of paneling that is pretty economical. A lot of buildings are done this way, and also keeping an eye on the deviation so that you know if the geometry can be applied, if the geometry really apply in this situation.